Okay, thanks everyone for joining this presentation. This is Tom. He worked with us for a couple of weeks after finishing his thesis. But since the thesis won an award from DAME as one of the best master theses, and I think it might be relevant for some of you, I asked Tom to, just to present what he presented for his master thesis presentation, plus a small tutorial on how to run transmission network expansion planning problems with the EU packages that we developed. So yeah, feel free to ask questions to Tom. I think he already defended his thesis, so he will be happy to reply to them. So I guess the presentation will be around the 20 minutes, and then we have the tutorial, which is 15 to 20 minutes as well, and then we should have some time for questions as well. Yes, that's it.
Okay, so my name is Tom Schoolmeesters, and I will present you my thesis. It was filtering relevant candidates from transmission network expansion planning, and I did an application to the North Sea. So before we'll dive into the details, I give a brief overview of what I will discuss today. First, a bit of motivation, then I'll talk about my methodology, then apply it to a case study, and end with the conclusion. And then, as Giacomo said, also a small tutorial on how to use the code. So why this topic? Well, the escalating urgency to combat global warming has driven the EU to commit to a net zero emission economy by 2050. And the cornerstone in this vision is the large-scale deployment of renewables, including offshore wind. And with targets reaching multiples of today's installed capacity, we're heading towards a more distributed, more reliable, and more uncertain energy landscape, which of course calls for major investments. And that brings us to the problem of a TNEP, a transmission network expansion planning problem, which is about identifying the most cost-effective network extensions. However, TNEP is a very complex optimization problem due to its immense scale. I'm doing it for the North Sea area, which is quite a large area. And also due to its computational burden, since you incorporate a lot of binary variables into the problem. And also adding to the complexity, traditional TNEP approaches typically rely on zonal models, where you represent a large bidding zone as one single node, so you can capture internal grid congestions. And also offshore and onshore optimizations are typically done separately, or with one of them heavily simplified, which also leads to suboptimal investments. So all these challenges have led me to conclude or to formulate an objective, which was the development of an effective pre- and post-processor that can identify the most promising investment candidates for offshore HV ceilings and onshore reinforcements in the North Sea area. And to give you a small example, if you have a 7-node system, you can already draw like 21 possible connections. If you then have a North Sea area with more than 1,900 nodes, in my case, then you can imagine that the problem really becomes computational intractable. So that's why we need a pre-processor to bring back the amount of candidates to a reasonable amount. So to support my objective function, I have 4 research questions. The first one is, of course, how we can select the most meaningful investment candidates. The second one is then on which node pairs offers the greatest cost reductions when connected to them. And then the last 2 are more about the effects on the cost, generation cost, and then the generation patterns, load shedding, and renewable curtailments onshore. Okay, so then my methodology, it's a very clear structure, although I try to make it a clear structure. So first of all, we start with an OPF to know the current state of network. Then we go to the key part of my thesis, which is the filtering of the candidates and then reducing the large amount of candidates to a reasonable amount. And then we end with the TNEP, which is then the final investment decision that is made via the optimization. Then along the process on the path, there are the yellow boxes, which are supporting tasks that are needed to make the case as realistic as possible, but also computationally manageable, for example, with the representative scenarios. Okay, so let's go over them one by one and give a bit more information about them. So first of all, it was the OPF. So first is zone OPF and then null OPF. Maybe you're wondering why I still do a zone OPF if I just said that it can capture internal grid congestion and it's not enough detail. But I only use it just to fix the cross-border flows at the boundary of my studied area. In that way, I doesn't have to take into account France and then all the other of Europe, and just can focus on the internal grids of the North Sea area in the null OPF, which then gives me a lot more information about internal grid congestions, power flows, power dispatch, nodal prices, a lot of information. Then some supporting tasks. So the OPF uses the most recent TYDP data of 2024 on demand and generation. Also, to cope with the large amount of time series, the 8,760 hours a year for the renewables, for the demand and the cross-border flows, I used a K-means clustering algorithm to group all the 8,760 hours into 15 representative scenarios. And on top of that, I also used importance subsampling to first extract 4 extreme scenarios, which represent key stress conditions on the transmission grids. Most of all, focusing on renewables and offshore wind for reliability, but also the 4th one is about the regional demand imbalance, for example, between the UK and then the mainland of Europe. This also there can be based on interaction. And then it's added with 11 regular normal scenarios to have 15 representative scenarios. And then a third change that I've made to the problem was the wind farm representation, because as you can see in the original network, the green dots are AC nodes where an offshore wind farm is connected. So the offshore wind farms are connected to an onshore AC node. And most of the time, there is also an AC load directly connected to it. So you have an offshore wind farm and an AC load without a transmission pod between it. And that's not realistic. So because you then can't have congestion issues between the offshore energy that is generated and then the mainland where demand is. So I decided to remove all of those wind farms onshore and to place a bunch of new wind farms, which is based on national plans and weather allocated right now, in the sea, and then group them into 2 sets. The one set, which I call 2030, which is just one set, which is already connected with the mainland via cable, and then another set of wind farms that is not yet connected or just islands. And then the optimization can decide whether it's connected and how it's connected to the mainland. And then you get a structure like this, where you can see that the offshore wind farms are now really offshore. Okay, then we can go to the key part of my thesis, which is then the filtering process. So first of all, you start just by combining every node that there is in the system with the 1.8 million connections that you can have. But of course, you can reduce that amount very quickly by just applying some very logical predefined rules, such as the maximum length of cable or line. I also only accept onshore DC reinforcements of existing corridors, so no new onshore DC corridors, and also I only accept AC offshore to connect a wind farm with the mainland. So the grids offshore is really a DC grid. With that, I can already reduce the amount of lines to 50,000 AC lines and 800 DC lines, which is still quite a lot. Then to assess the impact of those scanned lines on the existing grid, I used power transfer distribution factors, with which I then make a power flow matrix. In the power flow matrix, you have the information of, for example, if you build line X, scanned line X, what's the impact on the power flows in the rest of the system in each line that exists already. So it's a very powerful matrix for my filtering process with a lot of information. Then, secondly, I also wanted to include an economical signal, so the nodal prices as economical signal in my preprocessor. As the nodal prices represents the marginal cost of adding 1 extra unit of generation to a node. And for the AC candidates, I compute an impact metric, which is then just an multiplication of the power flow matrix that I had times a lambda vector, which is just the price difference over every existing line in the system. And then you can get an impact metric. So for example, if you have a line when it's built and it's having a large impact on power flows on existing lines, which exhibits large price differences, then you will have a candidate line with a high impact metric. Then for DC candidates, I did another thing because the DC grid is less meshed than the AC grid, and also it's more capital intensive. So I computed a benefit to cost ratio in which the benefit is the price difference over the DC line times the power that is expected to go through it, and then divided by the investment cost of the line. Okay, so now I have 2 metrics, and then you could say, okay, from the 50,000 AC lines and 800 DC lines, just pick the top ranked X% based on those 2 metrics. But yeah, of course, selecting like 100 candidates out of 50,000 is way too restrictive, since a lot of top ranked candidates will group around the same node in the system, which exhibits very high prices. So to have a more diverse and more realistic set of candidates, I introduced an extra filtering step, the candidate clustering, and in which I use the power flow matrix again, and a k-means clustering algorithm to group candidates in sets which have a similar impact on the power flow in the system when built. And yeah, maybe after presentation, I have a nice slide with some figures that I can show how it's then such a set looks like. So then I can reduce it from 50,000 to 2,200 AC lines and 200 DC lines, which is already okay. Yeah, and then from these numbers, I can select the top ranked candidates, the 5.5% top ranked AC candidates based on the impact metric, and the 12% top ranked candidates based on the B2C metric. And then I have those numbers. I also selected 10 random AC candidates and 5 random DC candidates. Is just to verify my filtering process, because if the filtering process would work perfectly, then these random candidates should not be built by the optimization program, because they just have a lower impact metric or lower B2C, so they should not be interesting. If they are built, then I know that there is something missing in my filtering algorithm. Okay, so now I can go to the TNAP and really solve the give a final investment decision. I'll explain that using the case study. So let's look to the nodal prices in the system. On the left-hand side, it's before anything is done, anything is built. And you can see there that, for example, in scenario 6, that there are some high prices or high price differences in the German-Swiss border, but also at the shore of Netherlands and Germany, which is critical to bring all your offshore wind energy on land. And then you can see that the filtering process really selects cables. The green are candidate AC cables, really cables in those areas to solve these issues. I also select these gains between different wind farms. And also the green lines here are, for example, lines with wind farms that weren't connected in the first place, but then the optimization program sees that it's interesting to connect them just because you have a very low price offshore and higher price onshore, so it's easy to connect them, or it's beneficial to connect them. Okay, so then I have a first answer on a research question that nodes exhibiting significant nodal price differences are strong indicators for potential transmission reinforcements. Now we have our candidate lines, so we can compute a mixed integer problem using the Google solver, and then we can go from candidates to effectively built lines, and you see again those 2 regions in which a lot of new lines are built. So let's analyze them, and then I can see that 39 lines are built out of the top candidates, but also 5 random candidates are built. So can I say that my filtering process doesn't work perfectly or doesn't work the way that I expected. Well, first I need to check the contribution to the objective, because if we check that, you see that all the random AC candidates contributes negatively, which means that if you build them, the objective function becomes higher. Yeah, which is strange, but logical. If you know that I allow a small error, an MIP gap of 5%, so that's why these things are possible. So when you have an MIP gap of like 0.001% or something, they should not be built. Also, the DC candidates here, they are contributing positively, so maybe there is still an issue. But then let's check a second iteration TNAP, which I mean, now you have a new grid with newly built candidates and the power flow is redistributed. So maybe now there are new lines which pops up to be interesting and lowering the objective function even more. So let's check that and do the process over again. And then we see again, there are a lot of lines built in the second iteration step. But again, also some random candidates. But first, an interesting thing that I saw then was that one of the DC candidates, the random DC candidates were built in the first iteration step, was now selected as a top candidate one and also built. So that was just a coincidence that was selected then as a previously as a random candidate, because in the second iteration pops up to be an interesting one. So that's not a problem in that opinion. But still, there is one which is acting positively, so maybe the DC precursor still has a bit of refinement to do. Regarding the AC ones, there's again one contributing negatively and then two other positively, but really in an order of magnitude lower, so they are not that important. Okay, so we can conclude that the method effectively identifies valuable investment options. If you recall that we're coming from 1.8 million candidates or 50,000 candidates, this is still working well, especially for the AC candidates, and for the DC candidates, maybe some further refinement is necessary to improve the accuracy. Then still two research questions to answer. The first one is about the cost impact. So again, on the left-hand side, you see the nodal prices with again those two regions now in another scenario, with again those high prices and congestions happening. And then you can see that their lines are built. If you see the impact on the nodal prices after the first iteration step, you see a large difference for the same scenario, just because there is a lot more wind energy imported, so the overall system price goes down, and also congestion issues in these regions are solved, which then of course results in a lower objective function. Then the second TNAP step, because you see that still after the first TNAP, there are still some regions which still have large price differences. So when you then do a second TNAP, you see that also these issues are solved. So that again proves the importance of doing a second iteration TNAP, as you also can see in the objective function, which is again lowered by 4 billion euros. Okay, so and also the cost impact question is that, of course, the TT grid expansion significantly reduces the generation costs. And then the last one was about the onshore effects. I think you already have seen that, yeah, the renewables are really boosted in the system and meeting 75% of the total demand. And if you see in comparison to reference scenario in which there are no candidates are built, you see that the amount of offshore wind is really high increased. So that's a good thing. That's why also the price went down. You can also see then the network performance indicators, such as the congestion index, which is a measure for the nodal price differences in the system. So for congestions on lines, you can see that this one is going down, which means that the system is used more efficiently than it was before. So then to conclude, I think I've come up with an effective preprocessor using nodal prices for AC candidates. For DC candidates, it also works well, but still some further refinement is necessary. And then also the second TNAP iteration, as you saw, is a crucial thing to do for further congestion relief And then in the last slide, you saw that, coordinated with expansion, improves system efficiency. Okay, and then, maybe some further research topics that I devised based on my thesis was, for example, here, that you could include additional assets such as converters, batteries, because it's not only cables you can plan, but also all the other things needs to be planned. And then if you do it combining, it becomes even more efficient. But of course, it's more binary variables, so the problem just become more complex. Okay, so maybe if you have already questions, or otherwise we do it after the tutorial. What you want?
Yeah. Anyone has questions?
I just
Not there.
one
Yeah.
thing. You mentioned that you do TNAP.
Yeah.
Are these TNAPs fed with the 2030 and 2040 data respectively, or each of the two is fed with both decades of data?
It's fed just the first TNAP. I think you mean by 2030, 2040, the two sets of wind farms.
Yeah.
Yeah, it's all done in the first TNAP. I use the two sets because there is a set which is already connected to it, to the shore, and then the second set, because I did the optimization, I did it for the year 2040 and 2050. So the wind farms that weren't connected are there, but just not connected, and the optimization program decides how you could optimally connect them to the shore. And then for the second TNAP, it's the same input data, but just now with a new grid. New build candidates that were built in the first TNAP are now also included, and then the second TNAP is done. Okay.
Yeah, no, for the second TNAP, you are considering you're doing all the reprocessing again?
Yeah, so you just start over with a new grid, you do the OPF, and then you again filter interesting candidates based on the new information from the new grids you have, because power flows are redistributed. So there can be new candidates that are popped up to be interesting.
In your results to show after your second TNAP, even there were still some high prices in the south of Germany.
Yeah.
What's happening there that still?
You mean, like this region? You mean?
Yeah, or in the south as well.
Yeah, there are indeed still some congestions that are happening. I didn't recall exactly what it was, but for example, maybe you could do here a 13 app to see if it's still necessary or it's still beneficial to solve them. It's not you can have congestions in your system. It's not the goal of my thesis to solve every congestion in the system. But yeah, it's possible maybe with the 13 app that also these issues are solved.
Maybe a second one. You mentioned that you used an optimality gap of 5%.
Yeah.
So I guess there was a duration issue of the.
Yeah, definitely.
So getting in, how long did it take?
For example, for the tutorial that I have now prepared, I ran it for 1 day, so 24 hours. But yeah, previously during my thesis, I had simulation running for 7 days with no results, and then I saw, okay, I need to do something, and then we filtered down the candidates a bit more, reduced a bit the MIP gap, so that I can have results, and yeah, because just a normal PC and no supercomputer. So, but I think still for 1 day for this size of grid, it's still okay. It's not that you have to wait very long. I did it on the server, so my PC was free, but yeah, it's still quite of time to do. It's not that you just click a button and you get directly the results.
Rest assured that the same issues also happen in European projects.
Yeah, probably.
Exactly one knows that.
I suppose one of the issues is also because when you write data set, you are basically working with the marginal cost of generation that comes into it. So the wind generator in Germany or cost in Belgium or whatever, and then there is, I think, just very lack of the function that results in will be everything integrating the economy. It's just 5% is not little.
Yeah.
Quite substantial.
Okay. Then I guess we can go to the tutorial.
Yeah. Okay. Maybe I'll check.
So yeah, about the tutorial, the idea was to make available the script that Tom prepared, since you might want to check TNAP problems or just how things work. And I believe it's also a good example that you can use to, for example, save figures or something. So then if you have master thesis students or new colleagues that are joining and they want to get started with the Julia, they can follow this script, I guess.
Maybe just a practical question, because I don't know how the tutorial looks like. If the tutorial looks like a script or something, or
So
to record this.
I'm recording the session. We have 3 different scripts, but also Tom prepared the documentation. So then you can follow, there are all the instructions that I will send around.
Yeah. Okay. So I prepared a document that maybe Jacob will also share with you. And basically, with my thesis, there are 5 documents related. So, of course, the thesis itself, then 2 repositories on my GitHub, which is the first one is the main one is EU grid operations, containing all the functions to do the TDAP and the OPF and all the filtering processes, and also containing all the input data. And then the PARMOS ACDC to really have the equations of the OPF and then the TNAP, etc. And then the other 2 documents are mostly notes of myself, also that I did now during my summer job, was to make this document with then explaining how you can do a test case and how you run it, and also then documentation with the code and all the functions itself, in which you have all the input parameters described, all the outputs for every function, and how the function works. But I will also show it a couple of minutes. Yeah, indeed.
What was that adaptation?
The adaptation was, maybe I'll show it directly, because I used representative scenarios. Because I used representative scenarios, I just made a copy of the function objective min cost, which is objective min cost representative, which then includes the factor. And the factor is it's just having the information about, for example, scenario 1 represent 586 hours of a year. And because the optimization need to know it to make its objective function for a full year. And it was not yet included, so therefore I needed to make a local version and add this function to that's the only thing I've changed, just to make that.
My suggestion was recently also just for the OPF problem itself, for instance, I made an implementation of a period OPF, like to set up something. If you create an issue and then maybe in that issue you post the link to that file, and then in the next version of file model is you can make sure that basically just delay factor is better. Then I will find a way of doing it more in a clean way. Just that we don't forget it.
Yeah.
Time being is fine. Then we can just.
Okay, good. So you have the 5 important documents. So you can find 2 repositories. Because I've made the adaptation of PowerMols. You can find them on my GitHub at the moment. They are public. So to start with, you just need to download them both, place them in the same folder and zip them. And then you can open the EU grid operations one. And in the directory, you can see here, so the data sources, which is just all the data for T1EP 2020, T1EP 24. Also, the relocation of the wind farms is also an Excel there. Important here is also, again, that because if you download it from our repository, you need still to download 3 links containing information about offshore wind, onshore wind, and PVs, capacity factors for a full year. and different climate years, etc. So that still needs to be downloaded and placed in the data sources file. That's all described in the document. So
just something quick.
Yep. Yeah, that's the plan.
Yep. Okay. Then you have the docs file containing the documentation of every function. I'll explain that later. Then in the scripts file, there is a test case folder containing 4 Julia files, which are basically the 4 files you need to run the test case or to run my thesis. And as you see, it follows the structure that I have explained. So first the zonal OPF, then a nodal OPF, and then a nodal TNAP, and then an extra visuals files, which is just, it's also an extra part of my thesis. To when you have the results, you need to get all the information from it and make nice figures, and that you can, these are all the functions that I used for that. So maybe I'll start with the zonal OPF and then just say a bit how it looks like and how you need to run it. It's basically just selecting it and pressing enter, but yeah, you have to make sure that of course you have a Gurobi license, because that's the solve that I use. Also, that your Julia version includes all the packages that is needed, but most of the times it gives like an error that you don't have installed it and you just need to install it. So it should not be a problem when doing it. So you just need to select all the things. Here is then information about the version of TYNP that I've used. Here it's 2024, it can also be 2020. And then the scenario of the TYNP that I've used. It can also be like the GA, the general ambition scenario for 2050, and another climate year can also be selected. Then this is all just loading the data and process them a bit. And then you come to the optimization, which is you can choose between 2 optimizations. The first one is an hourly optimization, which just takes the 8,760 hours and solve them in a full file and saves them as one file. But it takes quite a long time, since the more hours you do, the longer it takes. So that's why we did a batch optimization and just divide it in 10 batches. So I advise to use that one. It's much quicker, and the program is okay with it, so it works a bit nicer. So then you have your result file, as you can see here, with the solve OPF from PowerModels, and then you can save them as a file. All the files that you save from the test case are also saved in the output folder. As you can see here, the zonal of OPF files with all the batches as then files, and then also the input file. So the zonal OPF is done, then you go to the nodal OPF, which is basically the same, just a bit larger. Again, all the packages that you use here the same, but then here it's important that you say which area you want to analyze. It's only Belgium or it's the whole of Europe. For me, it's Belgium, Netherlands, Germany, then the western part of Denmark and UK, so the North Sea area. Then to do the relocation of the wind farms that I did, here that's like, okay, relocate wind farms is true, and also a detailed wind farm representation is true. So then here, when this is run, it deletes all the onshore, offshore wind farms and place them in a real location offshore, which is then done here. Also, as a workaround, I added on every load bus a value of lost load generation, just with a very high price to work around the fact that there can be load curtailments. So that's why there's a function also adds value of lost load generation.
Yeah, just stating the new version of PowerModel, you can actually remove the curtailment, but that might not be necessary.
Okay, perfect. Then
What do you mean with offshore wind farm relocation?
The relocation of the wind farms. It was the fact, I think, maybe I'll show the slide again. It's what I did around here with the wind farms that were located onshore in a not realistic location, directly connected to an onshore AC bus. So I removed all the onshore wind farms or onshore offshore wind farms, because there were offshore wind farms that were placed onshore. It's not realistic. So I removed them, everything, and placed them at a real location, following national plans offshore, and then connected them with a cable to the mainland. So you can have like this grid. This is then the relocation that is happening.
So replacing the levy.
Yeah. It's basically indeed, and also it became more offshore wind farms. It's really, I think, 200 wind farms, more detailed, with also power ratings that are related to the plants that are going to be built. Of course, there are still a lot of assumptions, but at least it's a bit more realistic than it was before. Okay.
Is it substantial? Because if you want to look at the growth of an offshore network, your offshore wind farms are placed before them.
Yeah. So then finalize the grid structure here. It's all just processing input data and getting the time series out of the files. Also scale the generation to make sure it's consistent with the T1DP data. And then again, you can do your optimization, your OPF for the nodal OPF. Again, there is a full time step simulation, which takes, again, quite a while. And since I'm working with a representative time set, you don't have to run this, but you go directly to representative time step simulation, in which then the reduced time series are generated, and you can do your OPF and have your results. So these are then the results for a nodal OPF. And maybe I can show, then you will again here, it's just saving the files. For example, showing a plot of what it looks like. So also every plot is saved in the test case folder under figures. Okay, and then for example, it was this one. For example, the figure of the representative time series that I've generated, just 15 time series, and for all the renewables, for example, scenario 2 was one with low renewables, scenario 1 was with high renewables. So that's such figure. There's also one for demand time series that you can show. Okay, then the third step is then the TNAP. Above there are 4 functions for my preprocessor. First, you need to generate all the candidate lines by combining every node and having the right power ratings, etc. Then also include cost data for them, computing the power transfer distribution factors in the power flow matrix to have your filtering process. And then the preprocessors, the candidates are filtered and then selected, and there is made an input dictionary, which is called zone grid, for the nodal TNAP. So I can show you then how such a zone grid looks like. Okay, this one. Now you see that all the yellow lines are DC candidates, all the green lines are AC candidates, the blue lines are existing AC lines, and the red lines are existing DC lines for the test case. Okay. And then again, 2 simulations, the full time step simulation, but that was the one that we didn't do because it takes too long. But we did the representative time step simulation. So for your 15 scenarios, you prepare your multi-network data, and then the MIP gap of 5%, you can try to make it lower if you have time enough. And then you get your results.
Curiosity, so just for these 15 representative types, how long does it now take?
Now for the thing that I did for the tutorial was 1 day. I think a bit, it was 20 hours or something. So then I have done it in beforehand on the server, so I didn't have to run it right now. So I can show you then, for example, here when you go further on okay, these plots, this is then showing which candidates are built. Yeah, I didn't know why it's here. It needs 24,000 seconds, which is 7 hours, but it ran longer than 7 hours.
Okay, so,
Yeah, yeah. Okay.
I would suspect that in the server, if you have a bit more RAM,
And then here you can see the build lines as you always saw in the PowerPoint with the 2 regions, which are regions where a lot of lines are built. Okay. Then still one thing or 2 things I want to show. Yeah.
Yellow ones are not.
Uh-huh.
We have a decent terminal of some sort of. Germany, Belgium, UK. No, Denmark, Belgium. This one.
Yeah, that's after the first TNAP. The second TNAP there is a.
Yeah, it's Triton, right?
Yeah.
So,
But it's connected via AC.
Yeah. I connect all the wind farms are connected via AC to the mainland.
that's not maybe very realistic.
Yeah,
Easy things
indeed.
to be done. I mean, there I think we just need to use some hard rules on power rating.
Yeah. Maybe also as an extra feature, you could say that. Now the DC lines are only between 2 wind farms, but it could also be that there is a wind farm going directly to an onshore DC substation, not via a wind farm.
What puzzles me a little bit is because this is not a candidate, right? This is an existing one.
Yeah.
If you have this wind farm that already gets full, so do you get anything additional through this action?
Yeah, normally I did. I don't know from heart the ratings of the cables, but I think I picked them large enough. Also extremely large, still reasonable, but I think.
Okay, it's not.
Yeah, it was not.
Wind farm, it's bigger, so there can be something.
Yeah, there can be something pushed through, but it's not that it's based on the rating of the wind farm.
Yeah. Because also then you have another multi-terminal, which is I guess this one.
Yeah.
So that's Netherlands, Belgium, and wind farms. So maybe this is already German. I don't know. It's still Netherlands. And there's another one again, UK, Belgium, I guess. And then UK back again with the. This one is one. Belgium, UK. Other one is another Belgium, UK. Yeah, it's hard to see which one is going there. This one is.
Like here's still a wind farm.
Yeah, because I think this one is going like that. So that's Belgium and UK.
Mm-hmm.
And there is this one. That's Belgium. I know that's UK to Netherlands, or no, that's already Denmark or Germany. So then there is the one that is coming here, also then goes.
Okay, then still one thing maybe I want to show is the documentation file and how you can reach it, because I wrote a lot of functions and it was at the end of my thesis, it was a bit scrapyard, but now I cleaned it. So I also made a documentation of it, so you can find it's also in the folder on docs. Then you on builds, and then you click on the index file, and you can go through all the functions, for example, to make your representative scenarios. these are then all the functions that I used with an explanation on the arguments that's used, the outputs, and also how the functions work. A bit more explanation on how it's done. Also for the test case, there are some documentation on how it's generally structured, what are the input parameters, and the expected output parameters. So you can have these, it's a lot of information just about every function that is created in the script. And then, maybe the last thing is then the extra visuals file, which just contains a lot of function to extract a lot of information about the results. Also, for example, this one is maybe nice, just to see your inputs data. Okay. So you can then see, okay, also for your 15 scenarios, how is the power dispatch done in the OPF? So that's a nice function, and also
the pie chart that you showed.
Yeah.
This, let's say, for the entire solution, to do it sort of thing.
It's for the entire solution, but it's not difficult to do it, to also implement it for just Belgium.
Usually all the applications, sort of this pie chart or is
Yeah.
and you can immediately see how the mix and other.
Yeah, it's not that difficult to also do that. Okay, and then last plot, it's also nice. You've seen a lot the plots with all nodal prices, which was very handy for me to know what's going on in the grid. And that's then this function like plot nodes with prices. And I've done it here for scenario 11, and then the result is well, it's this one. Oh, that's a legend. See that? Voilà. Now you can see for every scenario you can get such a figure to see the nodal prices and see what's going on and where there are high prices to see easily, okay, there is something on, some congestions to analyze the results. Okay.
Another legend and the separately.
Yeah, it's done. It's generated separately. I could not, because the color plot I didn't know how to put it on the same figure. Okay, I don't know if you have questions regarding the code or how you access it, and maybe also a thing with the power models AC/DC is that you always have to, before you do the TNAP, you have to let know power models AC/DC the representation of the time steps. So you need to copy your factor in the power models AC/DC objective file and then save it, and then it's okay.
Yeah, I think this is something that just
Okay, and as I said, Tom prepared the documentation he was sharing. So not only the documentation, but the instructions on how to use this. So we share it after
like this file.
after this meeting. And also, I mean, take it also like these repositories. There are quite some nice functions that you can use to plot stuff. I mean, it took me some time to retrieve some of the functions from people that are not with us anymore, back in the days. So please, if you needed to plot something, check also these things.
especially the one with the marginal. Something a lot of.
Okay, then thanks. Thanks for attending. Thanks, Tom.